All right, so we have a couple of miscellaneous topics for just a couple of days. Today, Monday, and then of course the quiz on Tuesday, before launching into a really big topic that will take most of the next month. Our first mini topic might just be like half a day. We're going to take another look at numerical integration and consider a few more strategies or recipes for numerical integration. But then we'll also probably start it for the next topic that is in non-obvious ways tied into that. We have one method so far for numerical integration with 3 sub-methods. So our one method for numerical integration is approximate the integral with a Riemann sum. And we're going to assume, as always, we chop things up into evenly spaced intervals. We need to pick some sample points. And so our 3 sub-methods are left endpoint, right endpoint, and midpoint. And we probably use midpoint the least because it involves a little bit of extra work. But we also saw some reason to believe it might be the most accurate of the 3. In examples like where f is monotonic, we know that one of these always overshoots, one of these always undershoots. The midpoint maybe is kind of the Goldilocks option. But these are the 3 options that we've seen so far. And to make better, if we want to get a better estimate on our integral, we need to choose a larger n. And that's the one lever that we have to pull at this point is, if I want to have a certain accuracy, I just take n to be bigger and bigger. All right. So there are a couple of other standard recipes for numerical integration that are not actually Riemann sums. That may be surprising at first because it seems like, well, what else is there? But these 2 methods that we're going to look at are slight modifications of the Riemann sum strategy. In fact, they can be obtained by averaging these 3 strategies that we already have. So we're combining a couple different Riemann sums. So for example, if we know that the left and right endpoints will often over and underestimate, what if we just average them? Okay. That seems like a way to improve. That average is not itself technically a Riemann sum, but it's built out of Riemann sums in kind of like a next simpler way. All right. So our first new method is called the trapezoid rule. And it says to average the left and right Riemann sums. Okay, so let's just do a couple examples and kind of draw pictures to see what this is doing. And I'll put up a computer illustration in a moment. Suppose n equals 1. I'm going to consider just a generic function. N equals 1 is going to be a pretty crude Riemann sum, of course. But suppose I have my function f, and I'm maybe integrating from a to b. And my first trapezoid rule says don't chop the interval at all. No subintervals. Just take it as it is. Well, if I just take the interval itself, my right endpoint Riemann sum corresponds to the area of this rectangle. So we call that R1, like R sub n for the nth right endpoint sum. The left endpoint sum is going to be the area of this rectangle. L sub 1, my first left endpoint Riemann sum. Now, when I average them, one way to geometrically interpret the average is it's the area of this region. If I take base times height, I average base times this height and base times this height, and it turns out that's the area of that blue region. That region is a trapezoid, which is where the name comes from, but it's just averaging the two rectangles that I get out of my left and right approximation. And we would probably guess that this is closer than either of them. If one of them undershoots, one of them overshoots, the trapezoid is going to average some of that out. So it's area of a trapezoid. Okay. Let's think about what happens with a different n. Maybe I'll draw a picture for n equals 3 of geometrically what's going on. And see what the trapezoids are doing. So this will just be on a generic function. Maybe it'll be similar to my last generic function. My generic functions end up looking like each other after a while. All right, so if I chop into 3 subintervals, like so, I could draw all 3 rectangles for the right, all 3 rectangles for the left, and so on. But to cut to the chase, what the trapezoid rule does is it uses a trapezoid on each interval. So on this interval, here's my right and here's my left. I'm going to estimate the area under the curve by this area. So instead of using rectangles like a Riemann sum, I'm going to allow myself just a slanty linear top that includes both endpoints. Okay. On this interval, I'm estimating the area under the curve by the area of this trapezoid. And on this interval, I'm estimating the area under the curve by the area of this trapezoid. Add them all up. Here's my estimate for the interval. So in one sense, we're giving ourselves a little more flexibility here. A straight up Riemann sum, you're only allowed to use rectangles. They have a flat top. That can seem like it causes a lot of error. If I say, well, okay, it doesn't have to be flat, it just has to be a line segment pointing any which way. The obvious choice being the one for the endpoints. Now we can get a much better fit to our curve. All right, so let's think about the formula that you would just throw your function into to compute. So the trapezoid formula for n. So if I chop into n pieces, I have these partition points. And I'm going to estimate my area by adding up this trapezoid, this trapezoid, this trapezoid. All right. So this trapezoid, the one way to express the area of a trapezoid is the base times the average of the heights. Sort of base times height with this averaging sense. So the base is delta x. The average of the heights, that's f of x0 plus f of x1 over 2. And that's the area of this first trapezoid. And similarly, this is base plus the average of the heights, f of x1 plus f of x2 over 2. And so on. Up through my last one, f of x n minus 1 plus f of x n over 2 times delta x. That's what I get from just adding up the trapezoids. Obviously, there's this common factor of delta x and everything can be written over 2. And then when I look at these f values, these y coordinates, most of them appear twice. x1 is the right endpoint of this interval and the left endpoint of this interval. So it's going to play a role in this trapezoid and in this trapezoid. Right? F of x2 appears twice, once as this right endpoint, and once as this left endpoint. They all get doubled except for the very leftmost and the very rightmost. So I have f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus 2 f of the next to last one, and then f of the last one by itself. So relative to each other, these y coordinates are being given different weights, different amounts of influence. Unlike a straight right, left, or midpoint Riemann sum, you take your ny coordinates and then you sort of add up f of them. Here I'm attaching weights of 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, which make my very left and right points half as influential as all the others. That's one way to think about this type of expression. Okay. So be ready to do this by hand on the next quiz. I can say, here's your function, n equals 5, trapezoid, go. You can punch it into your scientific calculator, and add up the numbers. I'm not going to go through that here in class, but be ready to do that. I'll show you an example with Desmos where you can kind of see it graphed out. And then I also want to start a little score sheet going for how this stacks up to the other methods. So I want to compare methods of integration with the same function and the same ends and kind of see how they're doing. All right, so let's look at the function integral 0 to 1 e to the minus x. This is one that we can do exactly. 1 minus e to the minus 1. Pretty easy integral. And let's look at how different methods do for, say, n equals 2, n equals 6, and n equals 20. So we already have right, left, midpoint, and now we're going to throw a trapezoid in the mix and see how they stack up. And then we also know the exact value, so we can compare everything to that. All right, so I'll actually punch out the exact value here, and then kind of fire up the computer and see how they do. So 1 minus, assuming I can find the exponential here, e to the negative 1. That's about 0.632. 120, 5588. All right. So that's what all these methods are trying to do. All right, I'm going to cover this up. Hopefully, back here in a minute. Let's take this thing out for a spin. I need a projector. All right, so this is bringing up the good old Riemann sum. Here's a left endpoint Riemann sum with n equals 2. And we have 0.803. That's a pretty miserable approximation. Suppose I crank it up to 6. 0.686, yeah, that's more respectable. And let's see what happens at 20. 0.648. So those are getting better, but even with n equals 20, that's wrong in the second decimal place. Not great. And you can see from the graph, right, we got a lot of area hanging over even with 20. What about right-in points? I mean, we wouldn't necessarily expect this to be a ton better. 0.616 here. And 0.581 here. And 0.487, truly awful, over here. All right, what about midpoints? And then I'll pull up the trapezoid and see how it does. So here, 0.625, wow, that's pretty good. So midpoints with n equals 2 is already about as close as these guys with n equals 20. It's kind of an impressive upgrade. What about with 6? 0.6314. And 20. Whoa! That's going to be a problem. All right, I need to reload the page because I think I confused it somehow. Oh, shoot. All right. That's x e to the negative x. 0, 1, 20, and c equals 0.5. This point, and okay, 63205. All right, so a midpoint with 20 is good to the third place, sort of off by like 0.0001 or 0.000, yeah. So way better. All right, so let's see how trapezoid does. It's got its own Desmos page and pictorial aids here. And you can see it's drawing the trapezoids and everything. So with n equals 2, oh yeah, sorry, I went ahead and 0, 1. So with n equals 2, we have 0.645. And what about 6? 6336. And 20. Yeah, how about just take 20? All right. 0.6321. 6321. Whoa, that's good to 5 decimal places, right? Not bad. So if you stack these next to each other, right, we can see that both of these are way better than right and left. And they're sort of comparable to each other. Here, we could go through and calculate all the errors and see how close they are. But here, we're within like 0.01 or so. Here we're more like 0.001. And here we're more like 0.0001 or something like that. So these two appear to be in the same ballpark. They trounce these guys, even for moderate size now. All right, so yeah, at this point you can't see the trapezoids very well, but yeah, that's what's going on there. Okay, so that simple idea behind the trapezoid rule, again, it's just a matter of let's average the right and left because maybe they're wrong in different directions. Great problem solving hack in general. Right? I've got 2 guesses. One was probably high, one was probably low. Great, average amount. That's powerful, it seems, based on that numerical evidence. Now, it may not be clear what to do next. We wanted it to get even better. There's a way of combining the right, left, and middle in a certain way. So, we have right and left by themselves. We have the average of right and left, which is trapezoid. And then we can have the midpoint that's off doing its own thing. The next idea is to somehow bring those together. And it's not as clear what's the best way to do it. I suppose we could average the trapezoid and the midpoint. Maybe that would do something. But it turns out the next step is going to look a little bit mysterious. And it'll leave some obvious questions hanging for a little bit. Where do these coefficients come from? Simpson says use left, right, and middle, or left, middle, and right, with relative weight one, 4, 1. So I'm going to take my y-coordinate at the left, 4 times my y-coordinate in the middle, and my y-coordinate at the right. So, for example, the n equals 2 case, I'm going to subdivide my interval once. Simpson's rule, by the way, always requires an even number of subdivisions because you're using both the midpoints. You're sort of taking midpoints of everything, so that chops everything in half. So I'm going to take this y-coordinate, and this y-coordinate, and assign them weights of 1, 4, and 1. So in the n equals 2 case, I would look at f of x0 plus 4 f of x1 plus f of x2, all divided by 6. This is like a weighted average of my y-coordinates. And then I need to multiply by the interval length, so times b minus f. More generally, if I start adding these together, again, the endpoints are going to overlap, like with trapezoid. The middle terms pick up these 2's because they're left endpoints of something and right endpoints of something.
Wouldn't that be n equals 1 because the midpoint?
Yeah, there's kind of a notational convention. I kind of want to call this n equals 1, but it's the industry standard to call it n equals 2. We're going to count the number of intervals after we chop with the midpoint. So just to be consistent with the book and everything. But we're going to have one main interval with its midpoint. So in general, if I do a 1, 4, 1 and add it to a 1, 4, 1, now I have 1, 4, 2, 4, 1 because that overlap got counted. So more generally, my nth Simpson rule, I erased my comparison chart. What was I thinking? Okay, my nth Simpson rule, I'm going to take f at the left plus 4 times f at the first midpoint, plus 2 times the next one, plus 4 times the next one, plus 2 times the next one. Right? So, because I think of this as like a 1, 4, 1 that overlaps with a 1, 4, 1 that overlaps with a 1, 4, 1, and then the very last one you don't have the overlap. So, your second to last point has a 4, and then your last point just has a 1. So you take this weighted average, so you're dividing by 3n down here, and then that's like your weighted average of your y-coordinates, and you go times your interval. So you can think of this in terms of, I'm taking a weighted average of all my sample points, That's sort of like my best average, sort of average height of my function, and then multiplying by the interval length. But I'm taking these weights in this particular way, relative to each other. 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Great, so that's a little more complicated. Again, be ready to just crunch a Simpson with your calculator on Tuesday. Once you do a couple, it's not so bad. There's a little bit to remember. You can always sanity check yourself. If you forget 10 or something, if I got an area of 30, do that graph of e to the x, I'd figure I need to figure out what went wrong. So let's see how this does on our exponential equation, the one that we're approximating. All right, so with integral 0 to 1 to the minus x dx, let's try Simpson. I meant this to be on the table, and then I erased my table. So n equals 2, n equals 6, and n equals 20, and let's see what happens. All right, so this is a Desmos Simpson rule thingy. And, let's call it 0 to 1. And I can see a result of 0.632 with n equals 2. So that's already good to like 3 decimal places, right? The very first Simpson one. Point 632.123 to 5. What was my exact value again?
0.6321205.
Okay. What's after the 05?
58.
So with n equals 6, I'm already good out to the 6th decimal place, it looks like. And let's throw a 20 at it. Hopefully it won't put in a billion zeros after I say 20. And I have 0.6321205.8 as opposed to 5 by 8. So that's good to like 8 places with n equals 20. Recall, the right and left with n equals 20, we're struggling to get a couple of decimal places nailed down. So something's going on here with Simpson that's giving us this massive accuracy boost, even relative to the trapezoid and midpoint. So there's an obvious question. What's the obvious question? Why? Why is Simpson's rule so accurate? And in particular, why does 1, 4, 1 seem to work so well? Right? We're taking this sort of system of weighted averages, and we're assigning weights 1, 4, 1 on the left, middle, and right. And this magic happens where we have this like crazy degree of accuracy. Well, we'll leave that hanging for a bit because our next topic is actually going to give us a way to answer that question. So for now, first thing, just be ready to crunch a trapezoid and a Simpson for points. But hopefully, this is provoking a little bit of curiosity as to why our integral became magically like orders of magnitude better if we threw a 1, 4, 1 at it. There's no obvious picture, like the picture of the trapezoid. There's no obvious arithmetic, like what's average and overestimate and underestimate. Something deeper is going on. All right, well, let's put that on the back burner for about a day, maybe a day and a half, and switch to another question. All right. So the next idea is improving on linear approximation. All right, so back in Calc 1, there's this notion of linear approximation, and I'll remind you of what the formula says. If I have a function, it's approximately equal to the value at some point plus the derivative at that point times x minus that point. And then, very important, for x close to a. Hopefully this looks at least kind of familiar. This is tied in with the definition of derivative, actually. You can rearrange this to a statement about difference quotients. It's tied in with the notion of tangent line. In fact, this is a y-coordinate on the tangent line. So this equation is a way of saying a curve is approximately equal to a tangent line near the point of tangency. It's not a statement, globally. I take this curve and this tangent line are not everywhere close together. But if I'm near the point of tangency, the curve and the tangent line are approximately equal. So that's linear approximation. There's a variety of problem types that come out of it. You can estimate different quantities. You can compute, do some error analysis. Various things grow out of this formula. So that's Calc 1. The thing that we want to do is figure out how to make this better. How to get a better approximation than linear. What do you think? Well, I can think about this algebraically. I have a certain type of equation here. This is like approximating my function as well as possible by a linear function, a function of the form like mx plus b. Well, if I'm thinking algebraically, I say I can probably improve things by adding another term. Right? What if I can have mx plus b plus some other stuff? That gives me the option of a better fit. I've kind of got more degrees of freedom to play around with. So algebraically, I might think, well, let's try doing this plus some correction that can help make up for the error in linear approximation. So algebraically, add a term. I could also think about it visually. This is trying to approximate my curve by a line. What if I tried to approximate my curve by some other curve that was a simplification of it in some way? So as an example, suppose I'm looking at e to the x, and I'm looking near 0. I've got my tangent line. And this is like the line that best fits the curve here. But I could ask for a next simpler example, like what's the best parabola fit? And maybe there's a parabola that nearby looks an awful lot like e to the x. And it's possible that the parabola will do a much better job of approximating e to the x because it's curvy, right? It looks a lot more like the e to the x curve. So visually, you might say, hey, what if I allow myself to use, say, parabolas? All right, so let's consider the question, what's the parabola that best fits e to the x near 0? Quadratic. Quadratics are parabolas. Best approximates this function here x equals 0. That's going to lead us into the idea of improving our linear approximations. Okay, so of course this is not quite a precise mathy question yet. We have words like that where we may not quite have a formula for what we mean. So one of our first orders of business is trying to figure out what we mean by best. And what kind of criteria should we use to say this is the best parabola thing, this is the best quadratic? What could we reasonably ask our quadratic to do? Or criteria, maybe we can have several. If I have a quadratic, I've got three choices I can make. I've got, say, ax squared plus bx plus c. I can pick A, B, and C. So I should be able to meet three criteria. With a line, you can fit two criteria, right? You've got mx plus b, you've got two choices. The tangent line does two things. It passes through this point, and it has the right slope. Its slope agrees with my function. So right value, right slope, two criteria. With a quadratic, I've got a third degree of freedom to play around with, so I could meet those two criteria and another one. So same value as f at x equals 0, and the same derivative as f. And I got one more. Is there a natural next step? If I'm thinking calculusly, maybe I can match the second derivative. Maybe I can have the right concavity. And at that point, I've used up all my choices. So I can find a quadratic that does those three things. That's going to be the best available. All right, so now we've got an algebra problem. We can actually solve what coefficients will meet these criteria and give me my best fit polynomial. All right, so the sort of steps to follow here. One, the form of the quadratic. Quadratic polynomial is going to have to look like q of x equals ax squared plus bx plus c. That's what a quadratic is. So our mystery quadratic has this form. I'm trying to solve for a, b, and c. Well, I'm looking at criteria on its derivatives and the derivatives of my function. So I'm going to calculate derivatives. Q prime and Q double prime. And I also have my function, and these are supposed to agree at 0. All right, so Q prime is 2ax plus b. Q double prime is 2a. My function's derivative is e to the x, and the derivative of that is e to the x. Not much going on there. So then I'm going to evaluate at 0 and match up to get a system of equations. So I want Q of 0 to equal f of 0. That's my first criterion. But I can calculate Q of 0 from this formula. A times 0 squared plus B times 0 plus C. And I can calculate f of 0 from its formula. F of 0 was e to the x. So c must equal 1, because they're both equal to these things. I'm going to write my criteria in the middle and sort of evaluate in both directions what each of those are. So this is supposed to be true. F prime of 0, that's e to the 0, which is 1. And f double prime of 0 is e to the 0, which is 1. And here, I'm evaluating these at 0. So 2 times a times 0 plus b, and 2 times a. Okay, so my system of equations, if I want to compress this, right, these middle terms were part of the logic, but the punchline is C is 1, B is 1, and 2a is 1. And of course, I can take that one step further to say that a is a half. So there's my coefficients. Conclusion. Is that my best quadratic, q of x, is a half x squared plus x plus 1. This is the quadratic that best fits e to the x near 0. All right, well, let's do a couple more examples, and we're working towards this kind of general definition. I can take this idea further, or more generally, there's no reason I have to stop at quadratics. I could add a cubic term, right? Find a cubic that best fits my graph. So what we're thinking about in general is polynomial approximations. Given a function, can I write down a polynomial that approximates it? I can pick some degree that I want to use, degree 3 through 5. And I can pick a base point. Do I want to approximate it near x equals 0, near x equals 3, near x equals a? So the general setup I want a polynomial approximation the title of this section. I called it Improving on Linear Approximation. So a polynomial approximation is how you can improve on linear approximation. Given a function f, degree n, and a base point a, we want a polynomial of degree n which approximates f near a as well as possible. Okay. That's what we're trying to do. That's kind of the general question that extends what we just did with this quadratic. And as before, our criterion for as well as possible is try to match the value of f and its derivative, and its second derivative, and its third derivative, and its fourth derivative, up to its nth derivative. Right? If I'm taking a polynomial degree n, I can get the first n derivatives right. And that's going to be my best fit. Jackson?
So you had like the 1/2 x squared plus x plus 1. So x plus 1 was the linear approximation. So was that the adding another term, or was that the same coincidence?
Yeah, exactly right. So Jackson's exactly right. So if I move from degree 1 to degree 2 to degree 3, I always keep what I had so far and then add another term onto it. So actually it would be more common to write it backwards, 1 plus x squared over 2, because I just took the linear thing and added a term. And you can think of the x squared over 2 as like a correction term. It sort of corrects for the fact that your function isn't actually linear. Then you add another correction to correct for the fact you're not actually quadratic. But you keep adding these higher and higher order terms as your degree goes up, and you end up with better and better approximations. So the t here is in honor of a person. What we're working with are called Taylor polynomials. So there's a mathematician named, I believe his first name was Brooks, not Brooke, but Brooks, Brooks Taylor, around the time of Newton, but really kind of pursued this idea of polynomial approximation. So that's why I use T, that's why I Taylor polynomials. All right, so we could go through the same logic that we just did with the quadratic and think about, what if I have an arbitrary function and an arbitrary degree and an arbitrary base point? How do I get the derivatives right? I'll just tell you the punchline. You can practice just computing these, and we'll kind of dive into more of the ideas here next time. The Taylor polynomial starts out with f of a, then you add f prime of a x minus a. So the first two terms are your linear approximation. Then I'm going to take the second derivative at a divided by 2 times x minus a squared. So I want to pause here and say a little bit about the form of the polynomial. If I say to write down a polynomial of degree 2, I might think a plus bx plus cx squared. Right? Quadratics have an x term and an x squared term. Actually, if I'm a little clever, I could write an arbitrary quadratic as something like this. It's maybe a less obvious choice, but all quadratics can be written in that way. If you think about it, you might realize any quadratic I could rearrange to have powers x minus 2 instead of powers of x. Well, if I'm looking at x values close to 2, this might make sense as a way to represent a polynomial. It's sort of based at 2 instead of at 0. All right, so I'm going to have this for my quadratic term. In the example we just did, the second derivative of my function at 0 is 1, so I had a coefficient of 1/2 of the quadratic term. The next term adds the third derivative of a and x minus a cubed, and now I'm going to divide by 6. This has to do with the fact that if I take x cubed and I keep differentiating it, I get 3x squared and then 6x and then 6. So when I differentiate it all the way down to a constant, there it is. What's the next one? What coefficient should I put in the denominator there? 24. Good. 4 times 3 times 2 times 1. So these numbers are what are called factorials. 2 factorial, 3 factorial, 4 factorial. Factorial means multiply everything up to that number. 1 times 2 times 3 times 4. And the reason is, if I say differentiate this term 4 times, the power rule brings down a 4 and then a 3 and then a 2 and then a 1. Cancels this out, and I get the right fourth derivative. So, plus dot dot dot. And keep going as many terms as you want up to degree n. So that's the recipe. You can check that a polynomial of this form meets our criteria. It has the right value, it has the right derivatives. So the first thing we can do is just compute polynomials. Here's a function, tell me a cubic based at x equals 3 that approximates it. I'm starting next time, but really kind of trailing through the rest of the course, we'll think about what you can do with these. There's a lot of things that are available once you have Taylor polynomials. That's it for today. Have a good weekend.